Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for UW Extension and Cooperative Extension. And on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Karsten Rhodes. He's with the Wisconsin IceCube Particle Astrophysics Center and was born in Hanover, Germany, and went to gymnasium in Hanover and got his undergraduate degree at the University of Hanover and a master's degree at Purdue University and his PhD at Purdue. Of course, I always have to point out that Purdue is the French past participle for lost. He also did, for his work at Purdue, he worked at the Fermi Lab, which is the French participle for closed. Then he went on to Penn State, where he joined IceCube, and then went to Ohio State. And then he's gone on to Korea, the university there that he will pronounce for us. And now he's back here at UW-Madison on a sabbatical. So I think he has covered 4 of the, are there 12 universities in the Big Ten? 14. That's why it's called the Big Ten, Tom. Okay. So I hope you're here to enjoying your time here in Madison. The lake will freeze over in a couple of months. You can go ice fishing. Looking forward to that. His talk tonight is on dark matter. Don't be afraid of the dark. And the cool thing is, the folks that are doing dark matter research are inviting us to consider October 31st every year, not just as Halloween, but as Dark Matter Day, or as I would like to call it, Dark Matter Night. And so I think it's great to have you here. I know nothing about dark matter. Let's let Karsten tell us all about it. Please join me in welcoming Karsten Rott.
Okay, thank you for the nice introduction, and it's great to see such a large crowd here to come out to know what dark matter is. And I think I have to disappoint you, because even after this talk you will not know what dark matter is, and the reason is that we don't know yet what dark matter is. But the question about dark matter is actually one of the most fundamental questions that we are trying to answer. So since the early ages of humanity, people have been trying to answer the question, what is the world made out of? And we have come a long way. So nowadays we know that everything in this room pretty much is made out of atoms. So, and we know that the atoms, we can decompose them in smaller particles. So they're made out of protons and neutrons and electrons. And even if you use a particle accelerator, you can break protons, and we can find that protons are actually made out of quarks, which are the constituents that make up neutrons and protons. Now, as we have built ever more powerful telescopes, we also started to observe the universe, and we wondered, what is the universe made out of? Is the universe also made out of the same matter that we have here, which we sometimes call the ordinary matter? So ordinary matter are the protons, neutrons, and electrons, and everything that we know about. So is the universe also made out of this ordinary matter? Now, as we observed the universe, we came along evidence that actually the majority of matter in the universe is not the ordinary matter that we know of, but it's dark matter. And that's actually why it is so important to answer the question, what is this dark matter? Because in order to understand the universe and to answer the question, what is the world made out of, we have to understand what is dark matter. And we have actually plenty of evidence for dark matter, and I will, during this talk, explain to you how do we know about dark matter, what do we know about dark matter, and then I will come to the question, how can we identify the properties of this dark matter? And since this series is called Wednesday Night at the Lab. I'm actually brought a picture of my lab, which is the IceCube Neutrino Telescope, located at the geographic South Pole, and this is actually the laboratory that I work with. I mean, not at, but I've been there a few times, but that's only a few special occasions when we get to go there. And during this talk, I will also explain you why we can use the IceCube Neutrino Telescope to look for dark matter and how we have searched for dark matter with IceCube. So now, let me begin with my talk, and let me give you the overview. So this is basically what I'm going to cover during the next hour here. So this is basically what I also just told you. So let's start with the first question. What do we know about dark matter? So we know from observations that the mass energy content of the universe, which is actually shown on the top right there, that the universe is made out of roughly 5% ordinary matter. So these are the protons, neutrons, and electrons. 27% dark matter, and then 69% dark energy. And I'm not going to talk about dark energy today, but that's also definitely a very interesting question. So what we know about dark matter is maybe that dark matter could be a new particle. And basically all that we know so far about dark matter comes from the gravitational interaction that it has. And maybe if you're a fan of Star Wars, then you maybe remember the scene where Obi-Wan is trying to find a missing planet in the star charts. And basically, he finds that the gravitational pull is pulling everything in the spot, but there's no star. So he concludes that, well, if the gravitational pull is there, then also a mass must be there. And this kind of resembles also what we know about dark matter. We know everything that we know about dark matter comes basically from its gravitational interaction. So let's go through some of the evidence that we have for dark matter. And let's start with rotation curves, or reviewing actually the gravitational law. So you can see a picture here of Isaac Newton and his famous gravitational law, which is shown here, which basically shows that F, the force that exerted between two masses, so in this case the apple and the Earth, is given by the two masses and divided by the distance squared times a constant g, which is the gravitational constant. So with this gravitational law, we can basically describe all the phenomena in our solar system, and we can also use this gravitational law to predict how fast a planet has to move around the sun to stay on a circular orbit. And this is actually the plot here on the right side. And yeah, so you can basically see that all the planets follow this gravitational or the prediction from the gravitational law. Maybe you think of Pluto, that Pluto is not a planet anymore, but of course also the asteroids and everything else, or dwarf planets in our solar system, follow the same gravitational law. Now we can actually ask, is this gravitational law universally true? So if it works well in our solar system, does it actually work well also to describe the motion of stars in galaxies? So on the bottom right, you see a picture of a galaxy. So this is a large spiral galaxy. And this galaxy consists out of billions of stars. And in the middle, you have basically a large mass concentration. And the stars are moving around this galactic center, basically. And the question we want to ask, well, are the stars in the system following the gravitational law. So some of the or the pioneering work on this actually has been done by Vera Rubin, sorry, and she actually measured the rotational velocities of stars in galaxies. She unfortunately passed away just about a year ago, which was very unfortunate because, I mean, of course, it's very unfortunate, but her she did a lot of the pioneering work on this, and also found a lot of the evidence for dark matter, and she was also considered for the Nobel Prize, and in particular, given that there are very few women who have won the Nobel Prize, it would have been nice if she also received that. So actually, let's have a look at her work to honor her. Now, she tried to measure galactic rotation curves. And to measure galactic rotation curves, she used the Doppler effect. So you know the Doppler effect basically from everyday life when you have a source of a sound, for example. So let's take this fire truck here. If the fire truck is moving towards you, the sound pitch will change then compared to when it's moving away from you. And the same effect is actually present in light. So you know that light is also waves, and these waves actually get shifted if the source is moving away from us or if it's moving towards us. And on the bottom here you can see an optical spectrum, and you can see some absorption lines in there. And depending if the source is moving away or towards you, you will see that these absorption lines are shifting. And so basically, if a source is moving away from you, it shifts more towards the red. And if it's moving towards you, it shifts towards the blue. So then on the right side, you can see that she looked at galaxies for which we had basically an edge-on view. And she then measured basically the color, or she actually looked at specific spectral lines, so at the H-alpha line from hydrogen. And she then basically could see how much these spectral lines are shifted. So out of this, then she can derive what are actually the rotational velocities in this galaxy. So this is a result that she found. She actually looked at many different systems, but this is just one example. So on the right side, you can see as function of the distance from this galactic center, the rotational velocity of the gas and stars in this system. And red is actually what you predict based on the gravitational law, and white is actually what she measured. So you can see that this gravitational curve actually stays pretty much flat, which basically indicates that there is more matter there than the luminous matter that we can see in this galaxy. And she did this measurement actually for many different galaxies. This is just some example of some of the measurements that she did. So this is one case where we have found evidence for additional matter that we cannot see. There's also other evidence, for example, through gravitational lensing. So if you observe large clusters of galaxies, as is shown here, and in the back you might have you look at the distant galaxies behind that, you can see that the image can be lensed, and you can see this sort of at, maybe let me see, where is the pointer? Okay, maybe it doesn't appear, but you can sort of see this ring shape, and these are actually galaxies behind this galaxy cluster, and they get distorted. And this distortion basically is based on the bending of the light due to the matter in between. And then we can actually check how much matter do we expect to be in between and how much bending do we actually see. And also from this you can derive that there is additional matter. Further evidence for dark matter, and actually one of its fundamental properties can be derived from an example which is called the bullet cluster. So this is actually a very beautiful image, but it's actually a composite image that is kind of false colors. But let me just explain what you are seeing here. So this is an example where two galaxy clusters, so two clusters of galaxies are colliding, and they are collided and actually pass through each other. And what you can see on here in blue is actually where the mass is distributed. So this is actually from gravitational lensing. You can obtain a distribution where the mass is located. And in red, you can actually see where the hot gas is. So this is the ordinary matter. So when these galaxy clusters collided, actually a lot of the gas was stripped out, and this is left in between, while the most of the galaxies basically pass through each other. And the matter is basically located at this blue region. Now, this actually tells us something about dark matter, because we can see from this image that dark matter did not collide with each other, but just pass through each other. So from this, we can actually derive this conclusion at the bottom that dark matter does not interact very strongly with matter, and also not very strongly with itself. Other evidence for dark matter comes actually from the structure in the universe. You can actually see a movie up here, which is a simulation of our universe. And you can actually see how the structure in the universe is forming. So actually these distributions basically shows the distribution of the galaxies and matter in the universe. And you can see that you basically get these filaments. So now let me actually move on to the next slide. I mean, this actually goes on for quite a bit, the simulation. But if we actually look at the distribution of the galaxies in our universe, we can actually find a structure that looks like this on the right. And on the left, actually, I have put different simulations of dark matter. And I labeled these, I used different names, cold, warm, and hot dark matter. So DM stands for dark matter here. It actually describes how fast the dark matter particles are moving. So for example, if I think of a very fast moving particle like a photon or light, which moves with the speed of light, then I would be in this regime of hot dark matter. And you see that the structure is very smeared out, which means that dark matter cannot be hot and also cannot be warm, but it's cold. And cold basically means that the dark matter is moving very slowly, or the dark matter particles are moving very slowly. Okay, so then there's further evidence for dark matter, actually from imprints to the cosmic microwave background. Maybe let me go quick on this. So this is actually a radiation that's emitted at the very beginning of the universe, and this has been precisely measured actually with the Planck satellite, and from this we can actually derive how much dark matter there is in the universe. Now let me move on. So one of the last evidence that I want to mention here for dark matter before I go to how we search for dark matter is actually evidence that comes from clusters of galaxies. So in this image here is the Coma galaxy cluster is shown. So each of these objects here is basically a galaxy, and we can also, again, using this method from Vera Rubia, when she looks at the redshift or blue shift of these objects, we can look at the velocity distribution of these objects. And if you assume there's more matter here, then the velocity distribution of these galaxies will be increased, so they will be moving faster. This is just basically what follows from gravity. Now this is actually when in the 1930s, actually Fritz Zwicky, who is a famous astronomer from Switzerland who worked most of the time at Caltech, he actually observed this Coma galaxy cluster, and he found basically the first evidence for this missing matter, or how he called it actually dark matter, or he spoke German, so he said dunkle Materie, so the dark matter. So this is a picture of him and the Coma cluster. So since these early days of Zwicky, actually we have learned quite a lot about dark matter. So there's conclusive, or there's overwhelming evidence for dark matter on all scales in our universe, as I have shown you. But the big question is still, what is this dark matter? So we have seen dark matter through its gravitational effect, but we want to know, what is this dark matter? So let's go try to answer the question, what is dark matter? Now from this observational evidence that I showed you, we can basically derive the following properties. So dark matter is cold, which means the particles are relatively slowly moving. It's neutral, which means it's not interacting through an electromagnetic interaction. So it doesn't absorb or emit light, because if it would emit light or absorb light, then we would have easily seen it. And it's also not very strongly interacting with the ordinary matter. So this, for example, we have seen in this example of the bullet cluster, where the two galaxy clusters are colliding. And also this new particle has to be stable, because if it decays, then it's not around anymore. So these are basically everything that we know about dark matter. So then we can ask the question, well, is there any particle that we know of that has these properties? So now here I show a table of all the particles that we know of. So this is actually the standard model of particle physics. So this is basically what you can find, or has been derived based on years and years of studies at particle accelerators and colliders. And these are all the particles that we know of. And as you see on the top right, the Higgs boson, this was basically the last missing particle in this standard model of particle physics. And we think now that this is basically complete. So we know all the particles that we expected, we have observed. And we can ask the question, well, is any particle in here, does it have the properties of dark matter? Well, so first we have to ask the question, are those particles stable? Or do they decay? And we can cross out actually a lot of them, because most of them actually are very short-lived, so you can only produce them at a collider for a very short time, and then they decay immediately. Also, we said that dark matter does not emit or absorb light, so it's not what we say electromagnetically interacting. So we can ask, okay, which both these particles are electromagnetically interacting, so we can cross those out. So then with this, now we are only with 3 particles left, which are neutrinos, but neutrinos are actually relativistic particles, so they move with the speed of light. So also we said dark matter should not be relativistic because it should be cold. So we can also cross these out, and there's nothing left. So the only conclusion that we can draw, dark matter has to be a new particle. And well, it's actually not so bad. I mean, to have a new particle, it just enlarges our horizon, maybe makes the world more interesting if there's a new particle. And there are actually plenty of theoretical physicists who have cooked up models that predict, for example, new particles, and just one of them is supersymmetry, which you might have heard about, but and people are looking for that. But there are also many other theories that predict new particles. So now, how can we actually look for this new particle? There are basically 3 different ways how we can search for dark matter. The first one is we can try to produce dark matter. So this is basically recreating the conditions that were present at the very early universe when it was very hot and dense, when we expect that dark matter was actually created. So, and we can do this actually at particle accelerators. So this is, or colliders. So in this case, we collide 2 particles with very high energy, and we can produce new particles. The second way how we can look for dark matter is actually through the scattering of the dark matter particle with ordinary matter. So this is, the idea is basically like when you're playing pool, if you have an atom and you have a dark matter particle coming in, it could hit the atom in rare cases and maybe give some nuclear recoil, and we can try to detect this interaction of dark matter particles scattering on an atom. And the last way, we can look for dark matter, what we call dark matter annihilation. So when dark matter interact with each other, it could produce maybe standard model particles which we then can observe. So now let's have a quick look at these examples. The first one, which we call make it. So the idea is here that we use 2 standard model particles that we collide at very high kinetic energies, and then use this energy to produce new particles. Now this is being done at the Large Hadron Collider at CERN near Geneva, Switzerland, and which is basically 2.7 or no, 27 ring circular accelerator in which we collide 2 protons, and these protons are basically moving with the speed of light and are colliding. And when such a collision happens, this is basically shown on the top right here, many particles are created, and out of these many particles that are created, we are trying to find a new particle. And the bottom right is kind of, or bottom left is kind of such an example from kind of a theoretical prediction for some new particles that might be produced there. So analyzing all this data is an incredibly difficult job, and at these experiments, which is for example shown here, the CMS detectors, there are really thousands of people working on this and sorting through all this data. And after sorting through all the data, they have found basically no evidence for a new particle. I mean, they have found the Higgs boson, so there's something, but there's no dark matter or no physics beyond the standard model, as we say. Now, the second way how we can look for dark matter is to look for an interaction of dark matter with ordinary matter. And this is what I call here shake it. So basically shake the ordinary matter. And actually outside here you can find a booth actually by Kim Palladino. So she's sitting over there, and later on she can since she is working on this dark matter direct detection, she can later also explain you more about this. But here I just want to give you the basic idea. So the basic idea is that this new particle, which I denoted by this Greek letter chi here, is just hitting an ordinary atom and depositing some energy, and we are trying to detect this small energy deposition. This is incredibly difficult to do because we know that dark matter is very rarely interacting. So to run these experiments, you actually have to go deep underground to be away from any backgrounds. So yeah, so later on, please check out the booth outside. Okay, and then the last way, and this is actually the way that I mostly look for dark matter, is through indirect searches for dark matter. So in this case, we assume that two dark matter particles hit each other, and in this process, standard model particles are created. And those particles we then are trying to observe. This is actually the basic idea here. On the top left here, you can see these two dark matter particles, or we call this WIMP dark matter here, weakly interacting massive particle, are hitting each other and then are producing some standard model particles. And at the end, you go through some decay chains, but at the end, basically, we can find stable particles that we can observe, like light or neutrinos or some antimatter. And there are different experiments that are trying to look for this or indirectly search for these signals. Now let me, I cannot go over all of them, so let me just pick the experiments that I'm working on, which is the IceCube Neutrino Telescope. So this is actually a picture taken at the South Pole. So this is actually the counting house where all our electronics are located for this experiment. Now, why have we constructed an experiment at the South Pole? Now, IceCube is a neutrino telescope, and in order to detect neutrinos, we need to make use of an effect which is called shrink of light. So this is actually when a neutrino interacts, it produces some relativistic particles which then send out some shrink of light. And this is actually a picture of shrink of light. This is actually taken in a nuclear reactor. And in a nuclear reactor, you have also some relativistic particles produced that pass through the water. And when they pass through the water, they send out this shrink of light. And basically, we are trying to detect the same light, but when a neutrino interacts with the ice. Now, now in order to detect this light, we need a detector medium that has very good optical properties. So that's why actually we decided to build the detector at the South Pole, because we can, at the geographic South Pole, the ice is roughly 2 miles thick and has very good optical properties. So that's why we decided to build a neutrino detector there. So then the idea to detect neutrinos through the Cherenkov light emission can be explained in this following cartoon here. So you have a neutrino, and that's coming in on the bottom right here. It's interacting, producing a particle which I call a muon here. So, and this muon is basically like a heavy electron. And when these neutrinos interact, in particular a high energy neutrino, it produces a very energetic muon, and this muon can actually travel several miles. And when it travels through the ice, it sends out a cone of this Cherenkov light. So all that we need now is a precisely timed optical sensor array, and with this precisely timed optical sensor array, we can then detect this Cherenkov light and reconstruct where the neutrino came from. Now this is a simulation here that actually shows this effect. So this, what you can see here are different strings of optical sensor modules, and this an energetic muon passing through this detector. Let me actually show this again. And as it passes through the detector, you see this Cherenkov light that's emitted. And whenever this light gets detected by one of the optical sensor modules, we mark this by one of these colored balls here, which basically indicates the time actually when the optical module was hit. And the size of these blobs basically indicate how much light was detected there. Now, this IceCube Neutrino Telescope is actually a multi-purpose experiment. It basically serves many different science or physics cases. Basically, we are trying to look for neutrinos of astrophysical origin. We're trying to study cosmic rays, atmospheric neutrinos, even glaciology, trying to understand the ice, and also look for dark matter. And of course, IceCube is headquartered here at UW-Madison, so maybe some of you know already a bit about it. So it's a very exciting experiment, and it's actually a very large international collaboration also. So there are about 300 people working on the experiment from all around the world, from 12 different countries, and all the countries are shown here. This is actually a picture of the South Pole where our experiment is located. This is actually the South Pole marker. This marker actually stands where the geographic South Pole is. And you can, if you read on there, you can actually read this January 1st, 2008. So this is actually at the time when I was there. So I took that picture. This is actually, yeah, some image of me there. So at that time, the gray in the beard is actually the frost, but now it became real. So it's time has passed on. So. Okay, so then the detector is located very close to the geographic South Pole. You can see basically on the top right there a map of Antarctica and where the geographic South Pole is located. And on the, basically you can see there where the geographic South Pole is, and also where the Amundsen-Scott South Pole Station is. So this is actually where the scientists live. Then there's a skiway. This is actually where we used to, or where planes come in to bring in supplies and scientists and to work there. And then very close to this station is actually where the IceCube Neutrino Telescope is located. And on the top left, you can see actually a temperature chart. And I haven't seen any winters here in Madison yet, but I hear that during this time here in November, December, we go to maybe minus 30 degrees at the South Pole, so maybe we reach this temperature here also. But you can see from this temperature profile then in the austral summer or austral winter period, it actually goes down to minus 70 or so, or even below that. And the IceCube detector was actually constructed during this period from November till February, so that's actually when the South Pole is accessible. So after that, the station basically is not accessible, and only a few people stay behind to keep the detector running. This was actually on this picture here, the guy in the middle, Tech. He was actually one of our winter overs who stayed there one entire year to keep the detector running. So they are doing a tremendous job, actually. Okay, so on the bottom right, you can see kind of this footprint where the IceCube Neutrino Telescope is located. Now let's actually go below the surface to see how the detector looks like. And you can see here in the schematic view how the detector looks like. So first of all, the ice is roughly 3 kilometers deep, and we have used a hot water drill to drill holes into this ice to a depth of 2.5 kilometers, and then deployed optical sensor modules. So in the bottom right, you can see actually such a optical sensor module. So it's basically kind of this basketball size module that contains a PMT or photomultiplier tube, basically a large light sensor. And with that, we want to detect the light from neutrinos that are interacting in the ice. Then this detector was built over a period of 7 years and has been taking data since 2011, ever since. Actually, already during the construction period, we obtained many very useful science data. Okay, this is how the detector would look like if you could float through the ice. These are actually the optical sensor modules. So it's basically at the bottom you can see this large optical or this large PMT, and then on the top it's basically just some electronics that digitizes the signal that's received by this optical sensor module. Okay, so then how do we look for dark matter with this neutrino telescope? Well, one of the most spectacular ways actually how to look for dark matter with IceCube, or very unique ways, is actually to look for dark matter that's captured in the sun. This is actually, it sounds at the beginning quite out of this world that this would be possible, but it's actually a very reliable way to look for dark matter. And the idea is here that you have dark matter particles from the galactic dark matter halo. So as we said earlier, the galaxies are engulfed in dark matter. So these individual particles could scatter eventually on or with a hydrogen atom in the sun. When this scattering happens, they can lose some energy and they can become gravitationally bound to the sun. And this is basically what's shown here in this pink line. So you have a particle that's bound to the sun, or this dark matter particle, and it will maybe this orbit brings it through the sun, and it has a higher chance of interacting again. It will lose more energy and eventually sink to the center of the sun. So if this process happens over millions of years, we basically accumulate in the center of the sun dark matter. And when you have an enriched region of dark matter, eventually it will also interact with each other. And when it interacts, it can produce the standard model particles. Now, from all these particles that are produced in the center of the sun, there are basically no particles that could make it out. Only neutrinos are the only particles that can make it out of the sun. So neutrino, I should have mentioned, are also called the ghost particles because they interact so rarely. So they can make it out of the sun and then come to the Earth. And if we detect such a neutrino with the IceCube detector and see that the signal points back to the center of the sun, then this is a smoking gun signal for dark matter. Now we have performed such a search, actually several searches. This is actually some results from the scientific papers that we have written on this. Basically on the bottom left you can see we are basically counting the number of neutrinos that we observed in direction of the sun. And this is actually what's shown in these black dots here. And this gray band is actually, maybe just look at the, one of this bottom region here. So, and this gray band is actually what we expect from a background, so from neutrinos that are naturally produced in the Earth's atmosphere. And you can see that this gray band, which is kind of the natural background, is basically flat, and the dots that we observe are pretty much just scattered around that, which means we don't see any excess of events or any additional neutrinos coming from the center of the sun. So, which is unfortunate, which means we have not seen any dark matter that's captured in the sun. Otherwise, also, if we would have seen it, you for sure would have heard about it already. So, and then on the bottom right is actually the results plot. So this actually shows on the x-axis. So on the horizontal axis, you have the mass of the dark matter particle. And on the vertical axis is basically the interaction cross-section, or how strong this dark matter particle would interact with ordinary matter. And this red line at the bottom, this is actually the result from the IceCube Neutrino Telescope. So it actually shows that the IceCube results are very relevant. So also on there are shown some other experiments, and you can see that the IceCube actually has some of the strongest bounds on dark matter. So we have not found dark matter, but we can still exclude some parameter space, which is then important for theorists who are creating models for dark matter to know kind of where there is no dark matter. So these searches are actually very, very important. There are many other ways also how we have searched indirectly for dark matter. So we have looked for dark matter annihilation in our galaxy, in the galactic center, in small galaxies, in galaxy clusters, and all those we have not found any evidence for dark matter. And similar, also other observatories observing with gamma rays, or they have not found any evidence for dark matter. Now, one of the things that we have, however, seen with IceCube recently is we observed very high energy neutrinos. This is actually following this, and also the completion of the IceCube Neutrino Telescope, we have also won this breakthrough of the year from Physics World. And this is actually a very big or important discovery, because for the first time we have observed energetic neutrinos from of extraterrestrial origin. So they are somewhere from outer space. And we still don't know where these neutrinos are coming from. So these neutrinos have humongous energies, so they actually have energies much higher than the energies that are created, for example, at the LHC, at the particle accelerator. Basically 1,000 times higher in energy are these neutrinos, or some of the neutrinos that we have observed. And the big question is where are these neutrinos coming from? So there are some natural or astrophysical source candidates like gamma ray bursts, active galactic nuclei, but also people have suggested maybe there's some new physics. So it could also be, so we're also looking if this high energy neutrino flux has any exotic origin or origin from dark matter. So, okay, so with that, actually I'm come to the end, and so let me conclude. So first of all, we know that most of the universe is made out of dark matter. So there's overwhelming evidence for the existence of dark matter, and I've showed you at the beginning of this talk the different ways how we have found the evidence for the existence of dark matter. So for example, in large-scale structure of the universe, galactic rotation curves, through gravitational lensing, cosmic microwave background, and so on. So there's overwhelming evidence for the existence of dark matter on all scales in the universe. And we tend to believe that this dark matter is a new type of matter that we have, a new type of matter, and we have found or we have identified certain properties of it. So it has to be stable, it's non-baryonic, not very strongly interacting, it's also not absorbing or emitting light, and it's stable and not decaying. And to understand the universe, really, we have to understand, or we have to learn what dark matter is. And that's why it's such an important, that's why it's so important to look for dark matter. And all these, there are intensive efforts now ongoing by searchers at particle accelerators, indirectly through looking for the annihilation of dark matter, and directly looking for the scattering of dark matter with nuclei. And through all these searches, we have we were able to already exclude some of the models that have been proposed to explain dark matter, but there's still plenty of parameter space out there to explore, and really we have to find dark matter to understand the universe and to answer the most, one of our most fundamental questions: what is the world made out of? And so I hope you enjoyed this talk, and also please remember October 31st, Halloween. no, it's the Dark Matter Day. So at that time you can learn more about dark matter. So thank you for your attention. Okay. Yeah.
Yeah, you mentioned something about using cosmic background radiation to determine the amount of dark matter in the universe. Could you say a little bit more about that and how that's done?
Yes, yeah. Let me actually go back to this image here. So this cosmic microwave background radiation is actually a radiation that was emitted at the very early universe, and it basically tells us about the density fluctuations in the early universe. And depending on if you add dark matter or if you add more or less dark matter, these density variations will actually change. And so what we actually measure is a power spectrum. So on this top right, the colors actually indicate like an overdensity and underdensity, or basically in its temperature, like a smaller or higher temperature. So it's actually very precise measurement. So the temperature variation is actually very small. So we can dissect this map or construct out of this map a power spectrum, and depending if you add more or less dark matter, this power spectrum will change. And I didn't bring the plot, but maybe later I can show you also. So, yeah.
You indicated that dark matter can tend to accumulate at the center of stars.
Yeah.
So I'm wondering, we had this recent experience, say in the past week or so, where these two dwarf stars collided. And so I'm wondering if there's any theory about what would have happened with the dark matter at the center of those two stars when they collided.
Yeah. So actually, so I think, so the question is, let me repeat, about dark matter accumulating in the center of stars, and then the recent event. So I think you're referring to the gravitational wave detection. So these are actually two neutron stars that collided, and the question is what happened actually to the dark matter, that, or if there's any dark matter also captured in the center of these stars. First of all, the amount of dark matter that's actually captured in the center of the sun or in stars is actually very small. So if you compare it to the overall mass of the sun, it's really minuscule. It's really many orders of magnitude smaller. So actually people have been trying to see if there's actually in the seismology of the sun, so basically through kind of pressure waves passing through the sun, if you can see any evidence for this dark matter that's captured in the sun. And basically, yeah, we cannot see anything, and the main reason is really that the amount of dark matter that's in the sun or in these stars is extremely small. So also with this recent gravitational wave events where two neutron stars collided, we wouldn't find any evidence for dark matter based on this. Or maybe.
So then, if it's matter and if it's in a star but it doesn't undergo any fusion reaction, or just is there and it doesn't participate in normal physics, I guess you'd call it?
Well, it participates in. So the question is, does the matter in the center of the sun or stars participate in any ordinary physics or interactions? And well, we know that dark matter interacts only very weakly with the ordinary matter. So most dark matter particles that would, from the galactic halo, that would impede on us would just pass through us. And also we expect that dark matter particles basically just pass through the entire Earth and only in very rare occasions interact. And basically for this dark matter that's captured in the sun, it's a very rare process. So it basically interacts with some atom, loses some energy, is on an orbit that brings it repeatedly through the sun and has a higher chance of scattering again and eventually sinks to the center. So it interacts with the ordinary matter, but it's just very weakly. So it's just a very rare process. And then once it accumulates in the center of the sun, then we expect, since the density becomes very high, that it also can interact with each other and then produce these ordinary particles which we can observe, like neutrinos. So. Okay. Yes. Yeah, is there?
I was wondering, with regard to black holes, since they interact gravitationally, and you talked about the only interactions you know of with dark matter is gravitational. Do you see any effects around black holes that could help explain what it might be?
Carsten, can you repeat the question?
Yeah, okay. So the question was if we can see from dark matter interacting with the black hole, if we can find anything about the properties of dark matter from this. And the thing is, I think that maybe we could learn something, but it's very very difficult to observe any black hole. I mean, even under ordinary circumstances, and so deriving any properties of dark matter based on such an interaction would be.
Now you have these interferometers that can measure the gravitational waves from colliding black holes.
Yeah.
Do you think there's anything there that would say something about the dark matter?
Yeah, so the question is, okay, with the gravitational wave detectors, can we say anything about the dark matter? And the gravitational wave, we basically just detect the two very massive objects spiraling in and then merging. That's what we detect with the gravitational wave detector. So we wouldn't know really what these objects are made out of, as long as they underlie gravity. But then also with a black hole, I mean, once ordinary matter or dark matter falls into a black hole, we don't really know what the state is inside. So it's not really anything that we would learn from that. So. Okay.
One of your first slides showed dark matter to be just a fairly small part of all the matter. And I sort of came into this thinking you were going to say dark matter was 75% of everything. But you've got this gigantic area that's dark energy. Is that associated with the dark matter somehow? Are those two paired up somehow?
No, I mean, it's basically, this figure basically represents that we only know about 5% of the mass energy content in our universe. And if you just consider everything that is matter-like, so the dark matter or the ordinary matter, then you can find basically that there's 5 or 6 times more dark matter than ordinary matter.
If you drop energy out of that globe, that pie chart, then you'd have a lot of dark matter if there was no energy in there. I mean, it seems like you're combining two things that don't combine. Put energy in the same chart as matter.
Yeah, I mean,
is that not true?
Well, it's sort of representing the mass and energy content in the universe. So the dark energy is basically just responsible for the expansion of the universe. And you could also, there are plots in which we just plot the matter content, and then you would see that, okay, we have basically 20% matter or 16% matter, and then the 84% or so dark matter.
Given how little you know about what how dark matter interacts with regular matter, what constrains the predictions that you make of an annihilation or a scattering event? So how do you determine what you think you would see if that happened?
Yeah, so the question is what, since we know very little about dark matter, what constraints can be derived from such an, or how can we predict such an interaction? And we basically know that dark matter was produced in the early universe. So in the very hot and dense universe, when the temperature was basically high enough, we expect that the ordinary matter basically was able to create these dark matter particles, and similar dark matter particles were able to annihilate and produce standard model particles. So we call this kind of a very hot, dense soup. And so this interaction that was possible, even if it was very small at the beginning of the universe, should be still present or possible today. So that's basically just a prediction from particle physics. So if there is a way that they can interact, then there should be still a way to for the dark matter to interact with matter. And all the searches that, I mean, that's actually, I showed many different ways how we look for dark matter. I mean, I showed this, this is, I showed the three different ways here, from production at colliders, scattering, and annihilation, but also there are basically many different ways how we look for these interactions. And many different experiments have different approaches. So that's why this field, I think, is so diverse, because we don't, it's very hard to predict how exactly dark matter interacts. But that's why we basically have to look in all possible ways. So. Yeah.
Since you haven't been able to detect dark matter, are there other theories that physicists have to explain the mass energy in the universe other than dark matter? Or are we all in on dark matter?
Yeah. Okay, so the question is, are we all in on dark matter? Are there other theories that are there other theories maybe that could explain dark matter without the need for dark matter? So one of the most popular ideas is actually that this the Newtonian gravity law is actually wrong, because we have gravity tested very well within our solar system, and maybe there are small corrections to the gravitational law, and so that it's not true, or that it's basically that we get faked into believing that we expect this this rotation curve to follow the red line, but if we change gravity, we can maybe get it to a way that it follows the white line. And there is actually a series there called MOND, or modified Newtonian gravity. And one of the arguments that is often made against this modified Newtonian gravity is actually this bullet cluster example. So with modified Newtonian gravity, you actually cannot explain this bullet cluster or other star cluster collisions. Now there's still some heated debate about this, because this bullet cluster example is just one example of galaxy or some clusters of galaxies colliding. There are other examples that maybe are not so clear, but still, given that we have evidence for dark matter on so many different distance or different scales, starting from small galaxies to large galaxies to galaxy clusters to the large-scale structure to imprints on this cosmic microwave background, we are quite convinced that it is actually a new particle rather than a modification to the gravitational law. Yeah.
I read an article last week, and maybe these articles come out every week, said that dark matter had been explained, that it was actually baryonic matter. It was so diffuse you couldn't see it, and apparently some team photographed and stacked a whole layer of photographs together. They claimed they could then see this baryonic matter. Is that the theory of the week, or is that a...
Yeah, so the question is if that last week there was some article that basically said that, okay, we don't need dark matter, it's just a misunderstanding of the baryonic matter. And well, again, I would answer to this that there have been many such claims that maybe we are not counting the baryons correctly. The same if you, like in this example of the maybe galaxy clusters here, if you count the or if you infer the baryonic matter, you basically infer the baryonic matter based on the light that we observe here. So you could say, okay, well, maybe stars are brighter or less bright, and we can explain in that way we don't need dark matter because the stars are just brighter or less bright or different stars. And normally you can always find, for specific examples, you can find ways around that you say, okay, we don't need dark matter, but then in order to understand or for a viable theory, we have to describe all effects in the entire universe. So we have to describe structure formation, we have to describe galaxy clusters, rotational curves, and there are many more examples. And typically these theories, they only describe one particular object. So I would be cautious. So I don't think the search is over. Okay, yeah.
I read the same article. It was called WIM, the name of the model, warm, hot, intergalactic medium. And what they said was that there was webbing, gaseous webbing in between the galaxies. And it was baryonic matter that was invisible because of the temperature. Because of the temperature of the gas, it was not producing X-rays, so we couldn't see it with the telescope. And also because of the temperature, it wasn't visible through light. If that helps.
Yeah. So so basically this was more common, basically, that this was called, or that the article was called the webbing. So it's basically cold baryonic matter in between galaxies that could not be seen through, for example, X-rays or and yeah, again, I think we might be able to explain the large-scale structure, but then there are probably other things that we cannot describe with this theory or this scenario. So I would still be cautious. So, and there have been in the past many examples similar to this. Yeah.
So,
okay.
is it known whether this dark matter is uniformly distributed throughout the universe?
Yeah, how it is distributed. Well, so this actually what I showed in this simulation actually shows how the matter and dark matter is distributed. So we expect that the matter distribution basically follows the dark matter because they are both of them underlie the gravitational force. So if there's somewhere a large dark matter density, then also you expect that ordinary matter gets attracted to these regions. So the dark matter distribution basically looks also like this cosmic web.
So then would you expect then that there would be a significant amount of dark matter within our own solar system?
Yeah, so the question is there a significant amount of dark matter within our solar system? And yes, so we there is some dark matter within our solar system, but the amount is relatively small. So the typical value that we have is 0.3 GeV per cubic centimeter. So this is 1 GeV is actually the mass of a proton. So it's basically a third of a proton per cubic centimeter. So this is actually what we expect as the dark matter density to be locally here in the solar system. And measuring the dark matter density within our galaxy, within the Milky Way, is actually quite difficult to do because the sun is kind of co-rotating with all the other stars, so it's more difficult to measure. But there have been measurements also that come to this value, and it's maybe there's some uncertainty with plus minus factor of 2 or so, but this is kind of the dark matter density that we expect here. Yeah. Okay, in the back there's one more.
So you said that dark matter was created in like the creation of the universe. So how was it made?
Yeah. So the question was how was dark matter made? Yeah. So the so how was the dark matter made? So we expect that the dark matter is a new particle that's probably quite massive. And so how was it created? So in the very early universe, the matter was actually, or the universe was extremely dense and hot. So we cannot think of individual kind of protons and neutrons at that time, but rather a soup of kind of quarks and photons and electrons that are all zooming around and hitting continuously each other and interacting with each other with very high energies. And at these very high energy collisions, we expect that also the dark matter particles were produced. And then these dark matter particles also interacted with each other and also annihilated, so produced the standard model particles again. But as the universe expanded, at some point the universe or the density became lower and lower, so that the dark matter actually what we call freezed out. So it didn't find enough other dark matter particles to annihilate and basically stayed around from these early days. So.
When you say very early, you mean like the first few milliseconds, first few seconds, first few hours?
Yeah, it's. I mean, it's difficult to speak about time then, but basically we expect that this. So it was basically before the cosmic microwave background was emitted, and this cosmic microwave background, I think, was at something like 300,000 years, and so it was I don't know if I have this. I had somewhere the evolution. Yeah, this plot. So inflation, quantum fluctuations. Yeah, so somewhere before this, for the dark ages, basically. We had.
Any other questions? One more.
I thought there was actually 3 types of matter. There's ordinary matter, dark matter, and doesn't matter.
Yeah, that's a good final word. So the comment was.
Thank you.
Yeah.